I will share this screen.
Super. And then maybe we do a brief introduction, Alexander. So welcome very much. Thank you very much for agreeing to give this talk. To give a bit of context, Professor Rothkopf grew up in Germany, undergrad at Heidelberg, if I remember correctly,
Yes.
and then PhD at the University of Tokyo, and is now a professor at the University of Stavanger in Norway. And again, for sort of broad strokes context, Alexander is just one of the absolute world experts on lattice simulations, especially as associated with quarkonia and the phenomenological applications of that to Pagi inclusions and many body QCD. So we're really lucky that Alexander found some time within his very busy schedule to talk with us today. So without further ado, please, Alexander, take it away. And
thank you very much.
Oh, sorry, one more thing. Do you welcome questions at any time, or should we save?
Yes, please. So everyone, please just feel free to just make yourself heard. I might not see you if you just raise your hand on the Zoom, and the organizers also alert me, please, if there's a hand that I'm not seeing. Happy to have it.
We're all friends here, so please take it away.
Very good. Thank you, Will and Heribert, first of all, for the kind invitation. I think UCT is a very exciting place to do physics research, and so I'm very happy to have the chance to talk to all of you. I'm very happy to have this opportunity to talk to you about a topic that has been somewhat dear to my heart for a few years now, and which I believe holds the promise of collaboration between otherwise rather distinct disciplines within physics, and this is open quantum systems, and particularly in the context of how they can help us measure temperature under extremes of temperatures. And so when we talk, when I talk about extremes of temperature, we could think of where in nature do we experience extremes of temperature, and two examples that very quickly come to mind for a hot place would be the sun's corona, with several million degrees of Kelvin being present. And on the other hand, outer space is surely a place that is cold, even though the cosmic microwave background gives us a temperature of around 3 Kelvin, even in the remotest locations of outer space. However, these numbers really pale in comparison to what you can achieve in the laboratory today, where it is now quite normal to reach temperatures as low as nanokelvin and even below. And this is associated often with the study of a form of matter, so-called Bose Einstein condensates, that are created from trapped ultracold atoms. On the other hand, with the advent of ever more powerful collider facilities, such as the Large Hadron Collider at CERN, it is nowadays possible to compress nuclear matter to densities and temperatures that are rivaling those present close to the Big Bang. So nowadays, in the study of so-called Quark-Gluon plasma, the high temperature state of nuclear matter in relativistic heavy ion collisions, it is standard to reach temperatures of around 10 to the 12 Kelvin. Now, I'm talking about temperature here, but what is temperature? So from this slide, you can see that I'm a theorist. And for me, as a theorist, temperature has something to do with the statistical distribution of energy. So if I have a system with enough interacting degrees of freedom, I can usually write down a so-called density matrix that consists of two components. One is it denotes the probability for a state with a certain energy to be realized in your system times the quantum realization of that state with a particular energy. And you can see that the letter capital T that we refer to as temperature shows up here in the probability distribution that tells us how energy is statistically distributed in this system. And so if temperature is related to the statistical distribution of energy, then measuring temperature has to do with measuring somehow the statistics of energy or any other temperature dependent observable in our system. And the most classic way how to determine the temperature of a system is what you would call a probeless approach, and usually what you would call it is it's passive imaging. You simply look at electromagnetic radiation emanating from the object whose temperature you want to determine. And this is an approach that has been known for millennia. So if you are a blacksmith in ancient Rome and you're forging the swords for the legions, you put the metal into your oven, and depending on the color of the glow of your metal, you know when it has reached the temperature necessary to be forged. In more modern settings, you would use, for example, active imaging techniques where you're sending light through the object or say the gas that you would like to measure the temperature of, and by the interaction between, say, the laser light that you're shining in and your medium, you would learn something about the statistics of energy, and by that on temperature. Now, besides the probeless approaches, there is also what you would call a probe-based approach, and this connects much more with how we measure temperature, so to say, in daily life, namely, well, the good old thermometer. So you have a small system, a probe system that you bring into contact with your medium or the system that you're interested in, and you wait a very long time so that both have equilibrated to the same temperature. You remove the thermometer and you interrogate it on its internal degrees of freedom, and that will tell you about the temperature of the medium. That is what we would call a static measurement of temperature. Then there's a different way, and that's the dynamic fashion of how to do this. Well, you still insert your probe you bring it into contact with the medium, but now you are observing over time how this small probe system moves towards thermal equilibrium with its surroundings. And the important point here is that this means that the probe does not necessarily have to be in thermal equilibrium with its surroundings. And if you calibrate this, then the speed, for example, by which you approach the same temperature tells you something about the surrounding medium. And so in both of these cases, the way how to determine the temperature is related to measuring or computing the non-equilibrium or the equilibrium properties of this small probe system. And so it turns out that in many modern applications, probe-based approaches are the way to go, and therefore we need, as a theorist, to develop an efficient formalism to describe the in-medium quantum properties of these probes, and this is where this open quantum systems approach comes in very handy. So now I've mentioned open quantum systems approach. What does it refer to? Usually it refers to a very generic setup of describing the physics of a small probe system coupled to a larger system, usually a thermal medium. And obviously the combined system of the probe and the medium is described, it's a closed system, and it's described by a Hermitian Hamiltonian, where you have a probe part of the Hamiltonian, you have a medium part of the Hamiltonian, and there's some interaction Hamiltonian, and those all together give you the Hermitian Hamiltonian of a closed system. Now, the statistical distribution of the degrees of freedom inside this closed system can be described by our good old density matrix for the total system, and this is nothing but what I refer to in the second slide. Now, if we want, yes, was there a question? No. So when there is, when you're asking for the time evolution of this closed system consisting of probe and the surrounding medium, then this follows the von Neumann equation that we are all familiar with, and that corresponds to unitary time evolution. Now, due to either so to say experimental limitations, we might not, or theoretical complexity, it might not be in our interest to describe the evolution of both the probe and the medium degrees of freedom together. So, and we would like to focus on the evolution of the probe itself. And purely formally, you can reduce your description to only focus on the probe by tracing out the medium degrees of freedom. So where you then arrive at what is usually called the reduced density matrix. So this now refers only to the degrees of freedom in the probe, small probe system. And well, the big question then is, what is the time evolution of this small probe system? The take-home message at this point is, without going into details, that this, because the probe is in contact with the surrounding medium, it can exchange energy. So this will not be unitary time evolution, but energy can be lost and gained from the surroundings. So this will actually correspond to dissipative dynamics, which goes beyond what you will be able to describe by a standard Schrödinger equation. And indeed, you will need a so-called dissipative master equation for the density matrix to capture this physics. Of course, everything has to be consistent, so that either you do the unitary time evolution on the full system and then you trace out the medium degrees of freedom, or you first trace out and evolve the probe itself, should give you the same in the end. And depending on the coupling between the medium degrees of freedom and the probe, there are different time scales that are involved in setting up such kind of master equations for your small probe system. And I would like to simply mention these up front. There's essentially three relevant scales that determine the nature of this evolution. And the first one is the medium relaxation scale, which essentially tells you if you introduce some sort of small perturbation in the medium, how quickly does this perturbation die down among the degrees of freedom. Then you have the intrinsic probe scale that is usually related to the inverse of the level spacing on the inside in your small probe system. And essentially it has to do with how quickly information is updated among the inner states of your probe system. And then there's the third time scale that's called the probe relaxation scale. And this one has to do with how quickly information travels between the probe and the medium. And you can think of it as if you throw in some small, like a point particle into a heat bath with a certain initial momentum. This probe relaxation scale is related to how long does it take for the directed momentum of this small probe to get randomized as it gets kicked by the surrounding medium. Okay, so this is a very brief rundown of some of the key vocabulary of what we will be encountering when talking about open quantum systems. And with that, we can actually start exploring how open quantum systems and the measurement of temperature come together when looking at the coldest matter in the universe. And this story begins in 1924 when Einstein and Bose investigated the statistical properties of bosonic particles, and they predicted that a new phase of bosonic matter would emerge at very low temperatures, which nowadays we call the Bose Einstein condensate. So if you have your lab and you manage to trap a cloud of, say, monoatomic uncharged atoms in your trap at, say, room temperature, then if you look at the distribution of momenta in that gas cloud, you will find a very nice Gaussian distribution that is just your regular Maxwell-Boltzmann distribution. What Einstein now and Bose now predicted says that below a certain critical temperature, a significant fraction of these bosons will actually condense into the ground state with a macroscopic wave function. And what that would look like is that, well, you would have you would have now these condensed atoms, essentially sitting in the ground state with zero momentum. And then around them, you have remnants of this Maxwell-Boltzmann distribution, which becomes narrower because the temperatures are now much lower than what they were at room temperature. This is so theorists can predict many things. In the end, one has to make sure that we can do an experiment to confirm or disprove this hypothesis. And this took a few technical developments that by now are quite famous. And the first one was laser cooling of atoms, and this exploits the fact that if you shine laser light on a monoatomic gas, which is appropriately detuned to a certain transition line for these atoms, then what happens is that if your atom moves in the direction of that laser beam, it can actually absorb a photon that gives it a recoil, meaning it makes the atom slower in the direction that it approached the laser beam. And then actually it will emit that photon at some time. But this emission is random. So if you have a lot of emission and absorptions where the absorption happens in a directed fashion and the emission happens randomly, then you get an overall net effect of slowing down this atom. And so this is really, you shine laser light from all directions. This induces this random emission of photons, and over time, this cools down your gas. And what you can achieve is temperatures of around 100 nanokelvin. However, this is not yet enough to see this phenomenon. And so the next decisive step was taken when it was understood that you can essentially evaporate off the high energy tail of your Maxwell distribution by modifying your trap potential. So if you now lower the trapping boundaries, some of the atoms can escape. So you're losing part of your gas, but the remainder of that gas is cooler, and you can do this multiple times. And that will leave you with a cloud that is now at a temperature of below nanokelvin. And that is where you can actually see these condensation phenomena happening. Okay, so we have done, let's say you in your lab, you have done this procedure. Now the question is, how do you measure at which temperature you are? And one common way to measure temperature is an active imaging technique. It's called the time of flight method. So imagine you have your cool cloud of atoms trapped in some potential, and now you remove that potential. Gravity is acting, so your gas will start to fall. But as it falls, there's still a distribution of velocities in these atoms present. And so as you start off with a distribution of velocities, that will actually mean that some of the particles, the atoms will have traveled farther than the others, and that as your cloud falls, and that means the cloud is actually expanding. And the expanding or the expansion rate depends on the initial velocity mixture in the Maxwell tail. So it grows, and then at some point you can shine light through this cloud, and you will be able to see how many atoms have essentially absorbed your light. You will see some shadow picture, and you can let it fall further. And again, you send light through it, and you will see that now, because it has diluted, there will be less absorption happening. And you can relate this change in the absorption to the original velocity mixture. And because the initial velocity mixture is determined by the parameter T, the temperature, you can now read off from these shadows that you produce. You can actually read off the temperature that the gas cloud had as you released it from the trap. Well, this is nice. We get an estimate of the temperature, but obviously there's quite a strong drawback to this method, which is that the system of interest is destroyed during the process. So you know where which temperature you were at, but you cannot reuse this system to now do a follow-up experiment. And only the other important part is only the non-condensed atoms that still were part of this Maxwell tail were relevant, and this their physics may be actually shadowed by this condensate peak. And to show you what one means by this is, and this is not just an academic question, is here's an actual measurement of this time of flight, and you can see here that at 54.4 nanokelvin, you have this peak that indicates the condensed part of your atoms, and then you see a remnant of this Maxwell tail, and you could fix this Maxwell tail and fit it to get the temperature. But you see that at 16.2 nanokelvin and 1.6 nanokelvin, there's essentially no remnant left of this Maxwell tail, and it's all overshadowed by the condensate. And so here's the first time that people have realized, using probes is a way how to get around the limitations of probeless imaging techniques. And whenever we talk about probes, we now have to face somehow the challenges of the experiment. And the challenge here is everything is too cold to touch. So you cannot just stick in a thermometer from the outside, and the probes that you want to use must be somehow embedded in the ensemble that you're investigating. So one way how this has been done is by using atoms that have a hyperfine transition structure. And so let's say the gas that we would call the majority gas is in a hyperfine state, MF equals -1. And now you can send in a radio frequency pulse to flip some of those atoms into a different hyperfine state, for example, into an MF equals 0 state. And what one finds is that these flipped states carry out some collective motion that people refer to as spin waves, and that these quasi-particles associated with these collective motions, they actually thermalize quite quickly with the surrounding majority gas. And so then you will have both majority gas and minority gas components. And since you have only flipped a very few of these original atoms into the MF equals 0 state, they are actually too dilute to condense. And you can imagine where this game is going. If I now use a different radio frequency pulse to weed out the original majority gas, I'm left with a collection of thermal MF equals 0 minority gas atoms that have not yet condensed because they're too dilute, but they're at the same temperature than the majority gas was. And you can do the time of flight with these. And so then what you get is a shadow picture like this here, where now it's only these impurities that you're recording, and they nicely show you this Maxwell-Boltzmann distribution even at 1.6 nanokelvin. And so here the probes were a precision enhancer for the measurement of temperature. Still, we are losing the system because we are doing time of flight on the minority gas. So is there a way to do non-destructive thermometry in the too cold to touch, under the too cold to touch restriction? And one clever idea that people are exploring is that whether it is possible to embed impurities in the ensemble that are of a different atom species. This is what people usually refer to as polarons. And so if you have potassium 39 as a majority gas, there's suggestions on the market to add a few ytterbium atoms as minority gas because they have a compatible structure, electronic structure that allows you to laser cool them together. And essentially what this would get you is a few very heavy ytterbium atoms sloshing around in a sea of much lighter potassium atoms, and that rings the Brownian motion bell. And since we're in such a cold regime, maybe even the quantum Brownian motion bell. So this is an interesting possible setup. And then the question, of course, is, well, what kind of properties of these embedded probes allow us to obtain the most precise measurement of, say, temperature? And this then becomes a question of metrology. And so one thing that in this community is then of interest is to ask, okay, what kind of observable is giving me the best estimate for, say, temperature? And what we have to think about is, well, if I want to have a measurement of temperature based on some observable, then this observable has a natural spread given by, say, quantum mechanics. Then, as we all know from introductory lab in physics studies, if I want to improve the uncertainty in my measurement, I have to carry it out multiple times, and that is the square root of n factor down here. And then obviously the error you make depends on how sensitive your observable is on the temperature. If you go to the extreme, if you have an observable that simply doesn't depend on temperature, then measuring it won't give you any reduction in your, or will not give you any information about the temperature. And so one would have to find a suitably sensitive observable here. Just as a comment, if you have a classical random variable and you're trying to improve your measurements, well, you're stuck with 1 over square root of n. But if you are in a quantum regime, there's actually ways how to carry out measurements that you can beat this classical bound for improving your errors, and that is called the quantum Cramer-Rao bound, where the so-called Fisher information helps you to beat this this measurement bound. And I don't want to go into more details here, just briefly mention that there's a lot of interesting concepts here when people think about how to devise sensitive observables. So from the point of view of the open quantum system, what is interesting to compute is, well, if we want, maybe we want to find out what is the most optimal observable to measure the temperature of our majority gas. And so that we can formulate as a optimization problem. We can ask, okay, which operator actually gives us the best sensitivity? And so the sensitivity is simply described as this derivative here. How large is the change in the expectation value of the observable if you change the parameter of interest? That is what this expression down here says, and you can actually write down the solution for this optimization problem in this form here. It's called the symmetric logarithmic derivative, and it gives you an expression for this most optimal observable that is called lambda t, or lambda. And here we ask for this in terms of the temperature, meaning what is the most sensitive observable for temperature, and that has to do with the derivative with temperature on the probe density matrix. So if you have access to the reduced density matrix of your system, you can now compute this most optimal observable. And for example, for the case of quantum Brownian motion of point particles, it has been found that the most optimal observable to measure temperature here would be to measure a linear combination of the position spread of these impurities and the momentum spread. And as a theorist, this is where, so to say, our work ends. We can determine the most optimal observable for a temperature measurement, and then we would now go and talk to our friends that actually do the experiment, and it might turn out that the most optimal observable is simply infeasible to measure, and then one would have to see and find a compromise of finding an almost optimal observable that is still experimentally accessible. Okay, so to get to this point, we would have to get an idea of what the density matrix, the reduced density matrix of our probe particles is. And I would like to use the next minutes to show you one concrete example, a classic and an iconic model of this open quantum systems, namely a heavy point-like impurity in a medium of harmonic oscillators. And you can ask, why harmonic oscillators? Well, because that's the one thing we can actually calculate. And so the system we look at it's your good old quantum point particle, p squared over 2m is the kinetic term. You have a bath of harmonic oscillators that we describe by the raising and lowering or creation and negation operators for each of the modes of this bath of oscillators. And then there's an interaction term which essentially couples the x coordinates of both your probe particle and the harmonic oscillator. Remember that in the harmonic oscillator in quantum mechanics, if you have a single harmonic oscillator, then there is a one-to-one mapping between the x operator and the p operator with the a and the a dagger operator. And similarly a, so here, this is the b operator, b plus b dagger is essentially the x operator of that harmonic oscillator. And so you're coupling here position of your point particle with the position of your harmonic oscillators. Okay, so this is the overall setup of the overall system. And now the question is, if I'm only interested in exploring the properties of the small point mass in that medium, what do I have to do? Well, we saw that the overall system evolves according to the von Neumann equation between the total Hamiltonian and the total density matrix. And now we have to trace out all the medium degrees of freedom, which here refers to tracing out the harmonic oscillator degrees of freedom. The first approximation that you will see is usually taken in this is the so-called Born approximation, which says that the total density matrix can be written as a direct product of the probe and medium density matrix. And that might sound as something that is rather, so say, very tight constraint, but actually it only makes a statement about the exchange of information between the medium and the probe, and it doesn't mean that the probe or the internal degrees of the medium have to be anything like weakly coupled. So this does not preclude strongly interacting systems to be coupled to each other. Then there are two approximations that in this particular case we can deploy. The first one is the Markovian approximation. That has to do with that you don't have to worry about memory of your system. And essentially it says that the relaxation scale is much larger than the medium scale. Remember, the relaxation scale was how fast does information travel between the probe and the medium. And so this says the medium updates much faster as information travels between the two. And this is why essentially you don't have to worry about keeping track of the past as you evolve this system. And then there's the Brownian motion limit. So we have not yet fully exploited that the probe is heavy. And this you do in this step where the probe time scale is assumed to be much larger than the medium time scale. So it's a slowly evolving object in a bath of quickly updating light degrees of freedom. This taken together, a lot of algebra, and in the end yields you an explicit equation of motion for the reduced density matrix. That is this rather intimidating expression down here, but there's a few important ingredients in this. So the first thing is that the evolution of the probe of the reduced density matrix, it has a coherent dynamics term. This would be the evolution of the probe essentially in the absence of the medium. Then you have the fluctuation part, fluctuation means that, or it's usually referred to a channel that allows you to pump energy from the medium into the small probe system. And then you have these two terms which refer to dissipation, and that is a channel that allows you to shed energy back to the medium. And of course, both of them are needed for you to eventually thermalize your probe with the surrounding environment. And while that was a success of theoretical physics to come up with this explicit expression, but then mathematical physics took a hard look at this and realized that there's actually a more general mathematical structure hiding in the quantum Brownian motion equation of motion, and that you can actually summarize the whole effect of this medium by one operator and one particular damping rate, as you would call it. And that is this so-called Lindblad operator that in the case for quantum Brownian motion of a point particle is just a linear combination of the x and the p operator. And you can then write down the evolution equation of your probe in this form. And it can actually be proven that any open quantum system that obeys a Markovian time evolution can be written in the form of such kind of a so-called Lindblad equation, where these Lindblad operators either sandwich your probe density matrix, or you have an anti-commutator in this form. This is okay. This is a mathematical structure. Why is this so nice to formulate it in this form? Yes, because you can prove that this equation conserves all the relevant properties of the density matrix during the evolution. Its positivity, hermeticity, and the unit trace that you need for the probability interpretation of the density matrix. And so for the example I just brought, you can do a sanity check of these equations of motion using Ehrenfest's theorem. And so the medium, the Lindblad operator, doesn't change the equation of motion for the velocity, so to say, but it adds an additional term for the force. So d dt expectation value of p now is proportional to p again, and times this what we called damping rate gamma. And now it also is clear what damping rate refers to. Damping rate really refers to the fact that the momentum of the initial momentum of your particle gets randomized, and so that the expectation value eventually goes to 0. And just to make sure that things are consistent with our expectations, if you look at the position spread of this quantum Brownian motion system, then what you will find is that for late times, the position spread actually increases linearly in time with a constant that depends on the temperature, the mass, and the damping rate. And this is really like the diffusion constant that you would expect in classical Brownian motion. Okay, and with all of this, all the ingredients are there to compute predictions for precision low temperature thermometry using these quantum Brownian probe particles, and you can compare with actual experiments. Of course, I've only shown you here a very simple case study. We've neglected possible memory effects, and so there are, of course, realistic systems where these memory effects are really relevant, and this is a current line of research in this field. Okay, so now that we've talked about the coldest matter in the universe, let's talk a bit about the hottest matter in the universe. And this story starts essentially in 1965, when the work of Hagedorn actually hinted at the existence of a new phase of nuclear matter as he was studying the statistical properties of the hadrons that were discovered at that time. And this phase is nowadays called the Quark-Gluon plasma. At room temperature, strongly interacting quarks and gluons are confined, as we call it, into color-neutral hadrons, mesons, and baryons. And we know from numerical simulations that at temperatures of around 10 to the 12 Kelvin in high energy physics units, this is around 155 MeV, there exists a transition, a crossover transition to a regime where quarks and gluons are not anymore confined within hadrons, but can travel over longer distances. The strong interactions have a particular property that is called asymptotic freedom, which means that at higher and higher temperatures, the interaction strength becomes lower. And that means that at very high temperatures, you will expect a gas-like weakly coupled gas of quarks and gluons. And this is what people have termed the quark-gluon plasma. However, it was quite a surprise to the community that just above the crossover transition, the quarks and gluons remain very strongly correlated and exhibit a behavior that is much more akin to a liquid. And this is what you would call the strongly coupled or liquid-like quark-gluon plasma that is currently accessible in experiment. And obviously, it's interesting to study the quark-gluon plasma also because it surely has at some point filled the universe after the Big Bang, and it might even exist inside neutron stars, or at least in the collision of two neutron stars. And the theory basis to describe all this physics is the quantum field theory of quantum chromodynamics, which is the field theory of quark and gluon fields that are carrying a additional new triple valued charge called color. And through historic reason, we call these then red, green, and blue, those charges. Okay, the quark-gluon plasma is studied nowadays in collider facilities around the world, where you collide the nuclei of heavy atoms under relativistic energies. And here, as an example, is the CERN laboratory, the Large Hadron Collider, its main collider facility here with its 4 caverns that house humongous detectors. Here, the Alice detector with 2 puny humans for scale. And the LHC operates in 2 modes. The first one is the reference, which is where you collide 2 protons. And so this vast amount of kinetic energy in these projectiles is transformed into new quarks and gluons that now give you a rather isotropic spray of new particles that emanate from this collision region. If you're instead carrying out a heavy ion collision, you now have a large number of quarks and gluons participating in this collision from within the projectiles, and that actually allows them to interact with each other in the collision center and form a hot collective state of quarks and gluons that we then refer to as the quark-gluon plasma. And because this initial state is rather anisotropic, now the interactions between those quarks and gluons imprint this anisotropy onto the spray of particles that eventually is measured in the detector outside. And by comparing the results of a proton-proton collision to that of a heavy ion collision, we try to now infer the property, first the presence and the properties of that medium in the collision. So if we want to understand the temperature inside of such a collision, well, the first thing that we can do is just look at the electromagnetic radiation that's emanating from your system. And this is a passive imaging technique where if you have a proton-proton collision, surely you will get some photons coming out of this collision, and we denote the momentum perpendicular to the beam direction as transverse momentum. And now if you do a heavy ion collision where you might be creating a quark-gluon plasma, you will have photons created at many different stages of this collision, and some of them, and they will escape essentially freely. Once they are created, they will escape freely to the outside. And so what one will be looking at is the photons out of these collisions. And let me show you here a rather busy plot, but let me try and guide you through it. You see 3 curves. This is essentially a measurement of the spectrum of photons versus this transverse momentum as they fly out of your collision center. And the different colored data points describe collisions, heavy ion collisions of different centrality, meaning how many nucleons are actually participating in this collision. And you would expect that the more central this collision is, the more energy is available to the collision center, and the hotter it gets. So At high PT, the photons are expected to arise from collisions immediately at the impact of the two projectiles, where there's the most kinetic energy available. And that means those photons will probably not yet have seen a quark-gluon plasma. And so if you compare a PP collision and a heavy ion collision, then the heavy ion collision for these photons will just look like like having added multiple proton-proton collisions on top of each other. There's simply more nucleons that participate in this. And this is what these black lines denote. The black lines denote the PP result simply scaled by the number of nucleons that are participating in your heavy ion collision. And you can see that for these so-called high PT photons, this upscaled black curve nicely fits the actually measured data. But what you can also see is that at low PT, there seems to be an excess of photons showing up compared to the black curve. And the one possible interpretation of this excess would be that, well, these might be photons that emanate from a quark-gluon plasma, and therefore they know about the temperature of that quark-gluon plasma. And so very brave researchers have now taken this data and fitted a Maxwell-Boltzmann distribution to this low PT regime, and lo and behold, they get values of temperatures between 300 and 400 MeV, which is much above this crossover transition temperature that I referred to before, that was 155 MeV. And while this was very encouraging at first, then theorists spoiled a bit the fun, because it wasn't clear whether these photons really come from a quark-gluon plasma, and people have come up with explanations of why you could get such kind of a excess at low PT, even if there is no quark-gluon plasma present. And so the question then is, are there other ways to measure the temperature? And this is where we come to a probe-based approach, because the challenge that we are facing here is that our system behaves too fast to watch. There's no laser system, for example, that you can use to probe a heavy ion collision. And so we really need to use the remnants of the collision itself as probe particles. And this is now my personal selection, of course, which particles to look at. And here I would like to focus on the pairs of heavy quarks and antiquarks, because you can, in the early moments of a collision, the partons have enough energy to create such kind of a pair of a heavy quark and antiquark. And similarly, as you know from quantum mechanics, introductory quantum mechanics, if you have two spin 1/2 particles, you can generate a singlet configuration and a triplet configuration. Here you have a tripled value charge that these quarks are endowed with, and so you can actually form either a color singlet or a color octet quantum combination of these heavy quarks. And such pairs are attractively interacting if they are a color singlet, and they are repulsively interacting if they form a color octet. And so if they come out as a color singlet, then they can actually form a bound state that is then referred to as heavy quarkonium. CC bar forms what we call charmonium, and BB bar what forms bottomonium. These are very interesting states because their decay into hadrons is highly suppressed due to their quantum numbers and the so-called OZI rule, which means that these particles have actually kiloelectron volt spectral widths, which means they live an enormously long time compared to the scales of the strong interactions. And the suppression of these hadronic decay channels also means that there is a significant decay into dileptons, so either electrons and positrons or muons and antimuons, which provides experimentalists with a really clean experimental signal to measure these states. And from a point of view of theory, these two-body systems are very interesting because they are non-relativistic, since the heavy quark mass is much larger than the intrinsic scale of QCD, usually referred to as lambda QCD, And that means that the intrinsic quantum fluctuations of QCD cannot spontaneously create a QQ bar, heavy QQ bar pair. And that means you can actually describe a lot of the physics of these bound states by a simple two-body potential that is referred to as the Cornell potential. And this is given here as a sketch. For very short distances, it behaves like a Coulombic potential that has to do with this phenomenon of asymptotic freedom. At intermediate distances, this potential grows linearly. That is a manifestation of confinement, that you cannot simply separate quarks from within hadrons. And then there is this potential becomes constant, essentially, because at some point you can store enough energy in the interaction, what we would call a flux tube between the quark and antiquark, to pop up out of the vacuum a new light quark-antiquark pair that is referred to as the phenomenon of string breaking. Essentially, it simply, for our purposes, all the relevant physics phenomenon that affect the structure of such a bound state can be captured in this type of a potential. Then you can see that there is essentially three bound states that this potential can sustain. And if you now look what emanates from your PP collision, well, as done here by the CMS collaboration, you actually find indications of all of these three bound states to be produced with different abundances in your PP collision. Okay, so this is nice. We seem to have a grasp of what is going on in the production of these particles. Now, what about a heavy ion collision? Well, again, we want to use the heavy quarkonium particles, and again, the building blocks, the heavy quark-antiquark pairs, they will be created very early on in the heavy ion collision, when there's enough kinetic energy still left in the projectiles to create these heavy particles. And they may then quickly form such kind of a quarkonium bound state. Then, at some later stage, shortly after that, the debris of the light quarks and gluons is expected to form this locally thermal quark-Gluon plasma. And that means now our quarkonium state, say a bottomonium, will now be immersed in this quark-Gluon plasma. And the question is, what happens to it? Can it survive this environment? Will it decay? Will it melt into its constituents? And that will influence the final distribution of quarkonium states that you will measure in the experiment. This is still interesting for theorists because of exactly the same reasons as before. This is still a non-relativistic particle because not only is the mass heavier than the intrinsic scale of QCD, but it is even large enough so that the ratio of the surrounding temperature with respect to the heavy quark mass is still smaller than 1. And that means, again, you have this situation of a heavy object moving around in this bath of light quarks and gluons. And again, the Brownian motion bell rings strongly here. And the first thing that has been known for quite some time is that the presence of the quark-Gluon plasma actually modifies the interaction potential. So this goes back to the works of Debye and Hückel in the beginning of the 20th century, where they understood for electromagnetic interactions that when you put static sources into a bath of charge carriers, of mobile charge carriers, that will lead to a screening of your interaction potential. And so, to the best of our knowledge, the potential in a thermal environment now becomes so-called Debye screened. You still have this Coulombic-like part at small distances, but then this will be exponentially cut off at larger distances. And early on in the seminal works by Matsui and Satz, it was realized that the screening by the medium will weaken the quarkonium binding and therefore may modify the production yields. the experts on quarkonium know, of course, that this is only half of the whole story, because the yields also depend on how many quark anti-quark pairs you produce. But for the sake of our discussion here, we are interested in realizing that this in-medium modification happens to the potential. And again, now you can repeat the same measurement as before, now in a heavy ion collision, and you will find that the spectrum that you measure for your quarkonium particles looks very different. So the red dashed line is the PP collision, appropriately rescaled, and you see that the ground state, you see some remnants of the ground state, but the first excited and second excited state, which are much more weakly bound than the ground state, they seem to be already gone at 5.02 TeV collisions. And of course, we would like to better understand this. And so we would like to better understand, how does a heavy quarkonium particle evolve in a thermal medium? And well, I showed you caldera Leggett for a point particle, but unfortunately, we cannot simply use caldera Leggett, because our probe actually has a finite extent. That's one of the important points. It's a bound state. It has internal structure, and it carries an additional color charge. And so one had to derive a completely new Lindblad equation. And here I would like to mention my colleague and long-term collaborator, Yukinao Akamatsu, who has made vital contributions to this field by deriving this quantum Brownian motion Lindblad equation from QCD at high temperature. Again, because it's a Lindblad equation, you can always write it in this standard form. And the first thing that happens is that, well, in this coherent evolution term, we find that the potential that governs this evolution is actually, as expected from general considerations, is a screened potential. And you can compute, at least in high temperature, where the medium is weakly coupled, you can explicitly compute this. Then let me just throw here at you the Lindblad operators for this system. And let us break them apart to see what is really going on. In QCD, when the quarkonium particle interacts with the medium, it does so by gluon exchange, and that induces both momentum transfer and a color rotation. And so here we are talking about the Lindblad operator that describes the effect of the medium on the quark and antiquark. That's why there are two terms with the opposite signs. And then there's also this color matrix. So that means that takes care of the color rotation that this exchange with the gluon brings. And you can see dependence on K, which is the exchanged momentum. And you can also see that there is some dependence on the center of mass momentum and the relative momentum between the quark and antiquark. And if you analyze the structure further, you can see that again, the physics of fluctuations is encoded in one part of this Lindblad operator, and dissipation is encoded in this second part here that depends on the momentum. The strength of the interactions between the medium and the quarkonium is governed by this function d here. That's the overall factor. And if you look at this function d in coordinate space, you'll find that it is nicely peaked. And when something is nicely peaked, as a theorist, I get excited, because that means that there is a scale hiding in plain sight, and that is the width of this peak. And that is what we call the correlation length of the medium. And that is a relevant new scale that governs these the physics of fluctuations and dissipation. And I see that I'm out of time, but I hope that you will bear with me for 3 more slides, and I hope to then be able to wrap it up soon. So what the physical processes that are hiding in this Lindblad equation are the physics first of screening, and this is a phenomenon that everyone is usually very familiar with. Again, if you have a quarkonium state that is bound and the screening radius of your interaction is larger than your QQ bar distance, then the gluon can nicely travel between the QQ bar and keep the binding up. Once the screening radius becomes of the same order of the size of the quarkonium or even smaller, then it starts to impair the exchange of the gluons, and eventually it will prevent the exchange, and by that it will destabilize the bound state. And this happens as you increase the temperature, the screening radius decreases. Now there's a different phenomenon that contributes to the stability, or rather the melting of the quarkonium state. And this is really something that you can explore when you formulate this in terms of these open quantum systems, and this is decoherence. And you can think of it in the following way. As long as the correlation length of your medium is larger than your QQ bar distance, then the color rotations induced by the gluon exchange act coherently on the quark and antiquark, turning a singlet state into a singlet state. However, if the color rotation is correlated only over a smaller distance than your interquark spacing, then it can start rotating the quark and antiquark individually, and that may change your color singlet into a color octet, and that is then repulsive, and therefore it destabilizes your quarkonium state, even though the screening radius might not yet have shrunk to a small number. And so we wanted to see where can we find first indications of these phenomena, and indeed we managed to do so by solving up to now. Unfortunately, thanks to COVID, things are we're slowing down a bit. But so what I can report to you here is the solution of the 1D Lindblad equation, where you can see here, we now start, say, with the ground state. That's the red curve. We start with 100% ground state and 0% first excited state in a thermal medium with the Lindblad equation and let this evolve. Or we start with 100% first excited state. Blue curve starts from 100% and 0% ground state, and we let it evolve. And what you nicely see is that in this Lindblad equation description, you at late times, you approach a universal steady state that is independent of the initial conditions. That seems to be already encouraging, but does this stationary state have anything to do with thermal equilibrium? Well, we can look at the distribution of states versus their energy, and if you do that at late times for different temperatures, and you plot it in a log scale, you'll find that the distribution of states, the occupation numbers, actually very nicely lie on a single exponential, and the inverse slope parameter of that exponential very nicely agrees with the temperature of the medium that we have immersed our quarkonium states into. And so not only does the Lindblad and the open quantum systems approach allow us to understand the different physical mechanisms better that shape the stability properties of quarkonium, but it seems to allow us also to come up really with a real-time description of the dynamics that allow us to quantum thermalize the quarkonium states. And this is actually the first time that it became possible to implement quantum detailed balance in any of these real-time open quantum system approaches and genuinely thermalize the quarkonium in a genuine quantum fashion. Of course, we have to work on this and implement this in 3D. And Takahiro Miura from Osaka University will have a paper out on that shortly. And so that is now an important step towards promoting the study of heavy quarkonium and heavy ion collision to a precision thermometry tool, that we have these Lindblad equation descriptions. And of course, here the caveat is that all the derivation I showed you was for weak coupling only, and we have to work hard. The community is working hard on putting this on a non-perturbative footing. And with that, I would like to summarize in this talk. I've tried to show you that open quantum systems are of interest in precision thermometry, where we use impurities at as quantum probes to measure temperature at vastly different energy scales, be it in Bose Einstein condensates or the Quark-Gluon plasma. There exists a theory framework to describe open quantum systems, for example, through the Lindblad equation that was originally developed in condensed matter physics, and that provides a common language now among formally disparate research fields. And for me, this is really opens exciting prospects for collaboration between ultracold atoms and heavy ion collision community on impurity physics, starting with quarkonium, but continuing in the context of jets, and even hadronization can be thought of as a phenomenon related to tracing out degrees of freedom. And with that, I thank you for your attention.
Super, that was awesome. I always feel like at least one person should clap, even in these virtual talks.
Yeah, one has to clap.
Thank you. Thank you.
Come on. This is the one thing that is really missing. Appreciation doesn't come through over the screen.
Yes, yeah, but I'm happy that we have the technology to at least have the virtual presentation. Yes.
Yeah. So that was really great. I have a bunch of questions, but
sure. Shoot.
Let me throw the floor open to especially the students, who this is a wonderful opportunity to interact with somebody, who's a real expert in their field that's not at UCT.
And maybe one explanatory note for the students, that such kind of a presentation is not put together in 3 hours on the day before, but is actually something that grows out of essentially 10 years of research activity. And just to put this into context for students, I'm sure you can find talks of me from 10 years ago that will look very different than this. And so please don't feel intimidated to just ask questions. I'm happy to answer if I can.
All right, quick question.
Sure.
So I know from looking at the QCD phase diagram that there's this, I think, open conversation about whether there is a critical point and where it lies. I'm wondering whether we can learn anything about that from looking at these impurities, since we're essentially looking at like hot matter on one side and cold matter on the other side.
So I think this is a very good question. I think there has been, there are research groups in the ultra-cold atoms community that are looking at the physics of triple bound states. I think this is something called Efimov physics, which would be a cold atom counterpart to having baryons. And then you can investigate what happens to these bound states in an ultra-cold quantum gas setting as you change temperature, as you go from one phase to the other. And so, yes, there is work that where the ultra-cold atoms community is trying to somehow gain insight into analogs of the QCD phase diagram. Maybe if we think about how is this done nowadays, well, the phase, if you want to investigate the phase structure of QCD, and specifically if you're talking about a critical point, usually a critical point makes itself seen through large fluctuations in your system. And so what people are doing right now is that they are trying to measure the fluctuations in certain observables, say baryon number fluctuations, as they scan the phase diagram by carrying out heavy ion collisions at different energies. And so they are trying then to figure out signals that that represent or that could indicate the presence of such kind of a second order phase transition from statistical analysis of observables in a heavy ion collision. So maybe short answer, yes, there are people working in condensed or in ultra cold atoms to build analogs of the QCD phase transition.
All right, cool. Thank you.
Sure.
Super, very good. Other questions? Well, perhaps in the meantime, while
Sure.
people think, so I guess I was really interested in all of this cold matter physics.
Mm-hmm.
I remember there was a guy in Carolina, I think Thomas,
Okay.
who was doing cold matter stuff, and he was looking at the viscosity of condensed things and all that kind of good stuff. But in any case, and that what you're talking about here reminded me of that. But I really liked how you talked about how there are these probes that they put in, and they can only sort of measure the temperature by destroying the system, and that led you to the proposal of almost salting your system. And then you got to the stage of this heavy atom that was going to look like Brownian motion.
Yes.
And then it wasn't clear to me whether there would be a way to measure that heavier atom without destroying the system.
I think that is part of the cleverness of that proposal, that you need to make the two species similar, so to say, they need to have similar enough properties that you can laser cool them together, but they still need to have different, they need to be different enough so that you can actually probe the one without interfering with the other. So I guess this would come down to, so since I'm not an experimentalist myself, I don't have any details on this, but I guess you would do some spectroscopy, so you some laser light to identify where your quantum Brownian particle is now sitting at, and so this should be a transition that is now different from the one that your majority gas is susceptible to, so that you can actually identify where those minority gas particles are sitting.
Yeah. I mean, sort of along a similar line of reasoning. So you talked about having these, I guess, hyperfine splittings, and you pump up one set to this higher excited state. Could one not watch that de-excite, and the rate at which it de-excites tells you something about the temperature, because you should know the ratio of excited versus not excited states?
So the ratio of excited versus not excited, usually I would guess we know in thermal equilibrium.
Right.
And since we have now moved it outside of thermal equilibrium, I'm not sure whether I'm getting the information there that would tell me something about the temperature directly, but it would maybe tell me about somehow maybe the coupling, an effective coupling between the spin waves and the majority gas or something like this. So the way how I understood this proposal is really that you would now in a very classical sense, you would follow your minority gas around and see how it spreads, how it diffuses, and essentially from that diffusion constant, again, you would read off what then the temperature of that system is. Yeah, so in some sense, so you're right in the sense that stimulated emission, so somehow de-exciting from one state into the other should be influenced by kicks. And so indeed, so some information about the environment properties should be one should be able to extract it from this de-excitation rate or so.
Okay, super. Let me see if anybody is again. I have one more question, but I don't want to monopolize. So I would like to encourage someone to ask a question.
So let me jump in here for a moment, and
okay.
also push at our students. Please, guys, speak up, right? So what I want to ask here is, in your treatment, it looks like your equations were intrinsically non-relativistic, largely based on the fact that you could do this with heavy quarks.
Yes.
Are there things that you could do with lighter particles where this is not good? Are there generalizations of such equations in that direction, or does it immediately become totally hopeless?
So, for example, for jets, people have looked at this soft collinear effective theory, where somehow you have the system can be formally turned into something that looks like a non-relativistic Hamiltonian. And so somehow looking at the small fluctuations around the velocity or the momentum in the direction of the jet, and there one might be able to deploy similar methods, but I don't think that the description of lighter mesons, for example, would lend itself. So there are of course phenomenologists who try to do exactly that. For example, there's the group by Ralf Rapp, who is trying to write down essentially an effective interaction potential for all quark degrees of freedom, be they light or heavy, and then do a quantum many-body computation based on that potential. But it is difficult to argue for such kind of a potential description to be applicable. Here you can systematically argue that the heavy mass allows you to reduce it to this form, but I don't think one could easily extend this to lighter hadron.
Yeah, I mean, I think you hit on it right there with the jets also, right? I mean, as long as you have a scale that you can smuggle into this,
yes,
that
exactly.
you can control externally, you can probably play a game that is not that terribly different from this.
Could I? Because I think I missed one point that I should have said. Of course, this all looks completely quantum mechanical here, but the origin of this formalism lies in a path integral formulation. So what one would usually do is one would start writing down the path integral of the theory, and then the tracing out that I've always written here in terms of a quantum mechanical trace would happen by integrating over certain degrees of freedom in your path integral. And this is known as the Feynman-Vernon influence functional approach. And then, as you say, once you have then some scale in there that you can form a small parameter of, you can then expand this influence functional around this small parameter.
Mm-hmm. Thank you. Very good.
Sure.
Okay, more questions.
So how far did you get with this quarkonium business? Are you at a point of making your own determination of what the temperatures that are reached at the LHC are?
Very good question. Unfortunately, not yet, because this is only 1D, and I'm waiting for our collaborators to finish the 3D version. And then, if you have the 3D version of the quarkonium evolution, then you need a model of the background evolution. So essentially what you're doing is you now know how to evolve your quarkonium in a certain environment with a certain temperature. And then now you need to model the environment that you would expect at a heavy ion collision. How does the temperature change over time? You take this model, you evolve the quarkonium in it, and then you get out a certain distribution of states that you would then measure, and then you have to figure out which kind of temperature profile reproduces these measured states. So there's unfortunately a little bit more of modeling still involved from setting up the quarkonium evolution itself to finally determining the temperature, because actually, obviously, a heavy ion collision is not really a thermal system that is nicely just sitting there, but it usually has temperature gradients and such, so that usually what you will be able to do is you can narrow in a certain temperature profile and how it evolves over time by comparing to the data. Thanks for the question.
Thank you.
Very good. Further questions? Well, let me then just ask my one last question, which might be naive. So when one derives the canonical ensemble and gets the partition function,
yes,
is that not already an open quantum system where you have your system and it's in contact with some kind of heat bath, and then you just throw the heat bath away?
Yeah, but I guess part of it is that you are somehow the logic is that you need the heat bath to get the distribution of states, and then you're turning off the interaction in some sense. And so since classical physics, in classical physics, in some sense, how to say, so this is, let's see.
You're sort of taking your system, you're putting it in contact with the heat bath, and then you're taking it away. Exactly.
And so this is a wonderful topic because it comes back to non-equilibrium quantum field theory, actually, to the question of do you need that external heat bath? And the answer, as far as I understand it, you don't need that external heat bath if you have enough interacting modes in your system that can redistribute the energy. So if you start off in quantum field theory with a out of equilibrium ensemble, and you have enough interacting degrees of freedom, or your degrees of freedom are allowed to interact, then what you will find is that, according to Boltzmann's H theorem, this will eventually go towards thermal equilibrium without the need for an external heat bath. The point, of course, is the evolution equations are time reversal invariant, so you will never be in thermal equilibrium, but for all practical purposes of experimental inquiry, you will be close enough to thermal equilibrium eventually that you cannot distinguish it from thermal equilibrium. So the construction, I think, the old construction from the 19th century, of course, didn't know about all of the error, so to say, the error of time problem and such. And for them, this was an idealized state, and you had to somehow prepare your system to be in this idealized state. And that's where this construction with the external heat bath comes from. But I think for us, we are not in need of this external heat bath in our modern understanding anymore. And it's just a helpful tool. And instead, what we will have is that if we were able to non-perturbatively solve the quantum equation of motions of our system, we would find that there's exactly one fixed point, and that is thermal equilibrium. And you will approach it, but you will never reach it. But for all practical purposes, as we see in the world around us, we often are close enough to it.
So, all right, so this inspired one last question for me.
Sure.
So the fact that there is an arrow of time and that entropy increases and that we see dissipation, does that somehow suggest that our universe is in contact with some heat bath that we've traced over?
Actually, I would have. So I think I think a bit, I should be careful with statements. To the best of how I understand it is that it is actually a matter of initial condition, that in the sense that, as I said, that if you start from some non-equilibrium initial condition, you will find that the system will distribute energy away from this non-equilibrium distribution, and as our quantum equations of motions show, that there exists only one fixed point, and that would be the thermal fixed point. And so in some sense, you can always reverse in some, with infinite experimental precision. Well, that's I should be careful. Yeah. So let's say it like this: if, of course, you cannot measure it, but if I ran a simulation, if I started with the correlation function out of equilibrium, I run the simulation, I could switch if I had infinite precision, I could switch the time, and it would get back to that initial condition, but it would, from the redistribution of energy, always approach closer and closer to thermal equilibrium. So somehow this arrow of time, seems to. So you get the entropy production once you do coarse graining on the level of the microscopic degrees of freedom. There is reversibility.
Yeah.
Maybe this is not completely answer the question.
So I guess it's the two parts. So one is that your system just naturally drives itself towards equilibrium, or something that looks like equilibrium. And the second part is the coarse graining.
Yes, indeed.
All right, that's super good. All right, well, I wasn't a completely silly question. Thank you for
No, not at all.
And one last call for anybody else willing to go out on a limb.
Well, if nobody does, then I will.
Okay. Sure.
There are. So you've been talking about systems with many degrees of freedom.
Yes.
But there is some evidence that you see essentially thermal distributions also produced in very few body systems, right? Electron-positron collisions, which have things that end up in final states with, again, not terribly many particles in it. But if you average enough of those, it starts to look thermal. So in the usual sense, there is no thermalization. There is nothing there that could thermalize in this traditional sense. Any comments on this?
Yes. So I'm not, unfortunately, I'm not completely aware of the most recent results on this, but there have been, I would like to mention two things. The first thing is that there have been ultra-cold quantum gas experiments to understand when do things allow a hydrodynamic description of their evolution. And in an ultra-cold atoms experiment, you can start with one atom, two atoms, three atoms, and so forth. And usually we would think, oh, we need a gazillion of atoms before we can do hydrodynamics. But I think the outcome was you need 8. So if you have 8 interacting atoms, the curve is already looking, I mean, you can predict what's going on using hydrodynamics. So the large number limit might start earlier than expected. So this was a I think Selim Joachim from Heidelberg. They looked at this and tried to exactly answer this question: how many degrees of freedom do you need before you would start to be able to use methods that we usually reserve for many body physics? That was the one thing, and the other thing was that there was some study about let me try and remember. This was related to trying to figure out whether seeing a thermal distribution in a heavy ion or in such kind of collisions might have a different reason than, so to say, statistical equilibration. And I remember that there was a work by Stefan Flörchinger, I think, who was making an argument that, and it actually had something to do with open quantum systems. I mean, it had something to do with that all measurements happen in the forward light cone of the collision, and if you then have the regions outside of the forward light cone, you can still have correlations with those regions. Obviously, there is no causal relation, but you can have correlations. And if you integrate out the correlations on the outside of your forward light cone in some very simple toy model, they showed that this could then lead to a thermal distribution inside the light cone. So there were some.
That sounds very interesting, actually. Do you remember the name?
I think this was Stefan Flörchinger. I will have to. Well, let's see.
I would be very much appreciative of a reference.
Yeah, I can. I will send you. I will send this to you.
Cool. Great. Nobody else yet daring to speak up. This is a very friendly environment. Nobody has been insulted, ridiculed, or anything. Not even me. Come on.
But also, maybe we have an opportunity in 1 week to, since I'll be back, that if there's some questions in the meantime after the talk, I'd be happy to answer them if there's any other questions that came up in the meantime.
Well, I think we can stop recording, and thanks again, Alexander, for a very stimulating.
It was a pleasure.
It was a lot of fun.
Very good. Very good. Happy to hear.
Exactly. Thank you so much. All right.